This video is the masterclass for P2 electricity for the physics, AQA GCSE physics paper 1. So this is going to cover the electricity module in detail, all the things that you need to know for the first paper. Let's get straight into it because there is a lot in this topic. In fact, electricity is probably the single largest topic that is covered on paper 1, or unless you kind of consider all of the various strands of energy across all the different modules. If you followed the masterclass on P1 on energy, you will know that actually there are three types of energy transfer: mechanical, involving forces, which effectively is the bulk of the topic for the P1 module; electrical, which is obviously the nature of this topic, so it's all exploring how do electric circuits facilitate electrical energy transfer via electric circuits, and then obviously thermal as the third type, which does cross over and touch upon some aspects of this. So that gives you an indication of what is covered in the module. I'm just going to very quickly show you some key bits of the specification. Feel free to pause the video during this bit if you want to read the specification. What do you need to know for the exam? First thing I just want to highlight to you is the circuit symbols. The first thing that you should revise if you don't know and are not super confident in the circuit symbols is please make sure all the circuit symbols that are featured there on the left hand side that you know and that you have revised, because all of those, it's not can come up but will come up. It's just on which page. And so we'll talk about circuit diagrams a little bit more later, but please make sure you know those. A couple of general tips. You will always, in pretty much every circuit, have to have a power supply, so you will definitely need to use either a cell or battery in basically every diagram that you will ever do. And note that all resistors start with the basis of a rectangle, and so when you kind of recognise that, you can see that there are 5 there shown that you can kind of see they've got some similarities. Anything that is variable has the arrow going through it. Have little ways of remembering them, like for example the thermistor is the one I always say that it looks like it's got a hockey stick going across it. And remember, voltmeters and ammeters, you're always going to include those pretty much in every circuit you more or less draw, and you have to understand the idea of ammeters being in series and voltmeters in parallel. We will circle back to that. Other bits of the spec, so you'll see, and I'll go through these in a minute, but a lot of the module is built around key concepts which have equations and some current voltage graphs, of which you can see several different types here that you need to know. I'll circle back to those later. You need to know about thermistors and LDRs, and then lastly know the difference between series and parallel circuits, and about domestic UK power, what that looks like, a little bit about resistance, and about mains electricity. Some easy marks that we're going to pick up at the end of this masterclass about what the different parts of a plug are, stuff like that. What's the difference between AC and DC? We can revise that really quickly and pick up some really easy marks. Okay, so those are the sort of final bits that we need to know. And quite a bit at the end about power and the national grid. You need to know a little bit about transformers as well and what they do. This is the section that's triple only, so obviously we're doing combined science, you can ignore this slide. The 2 sections that are triple only are electric fields and static electricity. They are not covered in detail in this video, so if you need to revise those, please use different videos to support, but everything else that's covered in this video is totally relevant for triple. Okay, so first key concept. There are 4 key concepts in particular that you must understand throughout electricity. I'm going to revise them all with you in a second, but first I just want to start with current and just understanding that first. So the first equation we have is the quit equation, Q equals IT. I always call it the quit equation because it looks like the word quit in my head. Q is the symbol for charge, and charge is any object that has an electric field is charged. So depending on the direction of that electric field depends on whether it's positive or negative. When we are talking about electricity, the vast majority of the time we're talking about electrons in a wire. We can of course talk about ions in a solution in electrolysis, but it's almost always going to be electrons in the wire. And so when we think of what current is, if we rearrange this equation to give us current, it's charge divided by time. So in other words, current is the rate of flow of charge. It's how many electrons are passing along the wire at a given point every second. So the best analogy for this is just imagine it like counting cars, like how many cars are driving down the highway at a certain period of time, how many pass me every second. So it's very much linked to the concept of number, which is really important. So you can very much relate it to the number of electrons passing down. But remember that time bit is important. It is to do with how quickly they go. You need to know the units of each of these things. Charge obviously is measured in coulombs. You don't need to know a great deal more about charge other than that. Just know that coulombs, capital C, because coulomb as a person is the unit, and current of course is measured in amperes. and A is the unit for that. There is an additional equation we might need to be aware of, particularly in some higher papers, which is you can work out the actual number of electrons by doing the total charge divided by the charge on one electron. Don't over worry about that on the foundation paper or the higher paper, just make a note of that. Okay, so just in terms of understanding this a little bit more clearly, so it's important you understand the basis of metallic bonding in a wire. So obviously wire consists of positive metal ions which are arranged in a lattice, which remember is just a regular repeating pattern, and they are surrounded by delocalized electrons. Those delocalized electrons, or free electrons, move freely through the wire, and as they do that, they have the capacity to collide with the ions. So this actually shows an electron that is not got a potential difference being applied to it. This is just a normal electron just bouncing around inside the wire. When a current is actually flowing, what you see over time is it starts to drift down the wire. So it's really important you understand the idea that these electrons are always colliding with the ions. And so one key phrase that's really important for this topic is the concept of electron-ion collisions. Now they will happen all the time anyway, like randomly, but anything that's going to increase the number of electron-ion collisions is going to increase resistance. And so one of the key bits of knowledge you need to acquire and be able to articulate, which we'll go through in a minute, is what's the relationship between current and resistance, and that's really, really key. So this shows the path of the electrons when there's no current, and when there is a current you can see it drifting down the wire. And obviously in the first example it's just due to the random motion due to the kinetic energy of the particles, and then when you apply a voltage or a potential difference, then it encourages the electrons to drift along the wire, and we get movement in a current, which is how DC current, direct current works, where all the electrons move in one direction. Here's an example of a quick past question on a higher paper that's come up, kind of testing the misconception of this. Take a minute to just kind of pause, read it through, have a little think. So just to highlight what the mistakes are here, of course it's electrons that move down the wire. If we're increasing the current, as we'll talk about in a minute, that will increase the temperature of the wire. And so in doing that increases the kinetic energy of the particles, and so the vibrations of the ions, it says in the actual question, makes the atoms vibrate less. I would definitely prefer it if it said ions there, but the ions will vibrate more when the temperature increases, and that will increase the number of electron-ion collisions, and that will increase the resistance. So this relationship between current, temperature, electron-ion collisions leading to an increase in resistance is really, really key. We're going to circle back to that several times. So, in terms of key concepts then, I've mentioned some already, but just to highlight them. So there are four main concepts that the vast majority of this topic can be summarised around, and a big chunk of it is just being able to use the equations for these concepts. So we have the equation for current, which is charge is equal to current times time. Charge is the rate, current is the rate of flow of charge, as we've already said. It's how many electrons flow down the wire per second, in essence. So when we say the word rate, we divide it by time. So it's important you know that's measured in amperes, and it's always measured by an ammeter in series. Now, the next one is voltage, but we have two types of voltage. We have EMF, electromotive force, and we have potential difference. When you think of voltage, I want you to substitute it in your head just for energy. So, because voltage is defined as the energy per unit charge. It's how much energy does each electron kind of hold. So the reason we have two types of voltage, which is electromotive force and potential difference, is energy has to go into the circuit and energy comes out. So EMF, electromotive force, is the energy that is supplied by the cell or battery that goes into the circuit, and potential difference is the energy that's coming out of the circuit via the electrical components like the bulb, the resistor, etc. And what goes in must come out. So the total EMF must equal the total potential difference. So if we've got a 12 volt battery that is being supplying power to an electric circuit, all of those 12 volts will have to be come out somewhere as a potential difference. That could be over one component, or it could be split across several, but it has to be the same number when you add it all up, because it's about energy. What goes in must come out, and that's the principle of conservation of energy. We're going to try most of the time, though, to use the phrase potential difference, not voltage, because in the vast majority of cases that's what you're going to be talking about. It's much more common that you'll talk about that than, say, electromotive force. So when we talk about potential difference is measured with a voltmeter in parallel. Try to just make that substitution change to not talk about voltage, but talk about potential difference. You will increase your marks if you do that. Hands down, the single most important equation in this topic is the equation for Ohm's law, which is resistance is potential difference divided by current, because it combines the three most important concepts in the topic, as we've already talked about, trying to understand this relationship between current and resistance, Ohm's law tells us about that. So the actual definition of this resistance is just the equation, so it's potential difference divided by current. But as we've already talked about, and we'll come back to this in a minute, when we understand resistance, resistance is really a measure of how much impedance there is of the electrons through the wire due to electron-ion collisions. In other words, how difficult is it for those electrons to kind of travel down the wire. Resistance is measured in ohms. There is such a thing as an ohm meter, which can be used to measure current resistance directly, but the vast majority of the questions you will deal with, you will use an ammeter and a voltmeter, and you will calculate resistance by doing potential difference divided by current. And lastly, power. There are actually 4 equations for power that are relevant to this topic. There is the general equation for power, which is listed up at the top here, which is the energy transfer divided by time. So when we're thinking about the concept of power, it's the rate of energy transfer. Power is basically how quickly we are transferring energy from one place to another. So the general equation is energy transfer divided by time, but there are 3 specific ones for electricity, depending on which of the 3 other variables at the top you know. So the simplest one is just power. Electrical power is current times voltage, but we also have I squared R if you know current and resistance, and V squared over R if you know potential difference and resistance. I want to highlight to you the I squared R equation because that one can sometimes be described as the power loss equation. The reason being the 2 things that lead to energy being lost are current and resistance, because both of those 2 things will increase effectively the number of electron-ion collisions and therefore increase the impedance of electrons. So they will result in power being wasted when those 2 quantities are increased. So understanding that current is kind of doubly responsible there is again key to this relationship between current and resistance, which we'll talk about several times. And power is measured in watts. Again, that's after James Watt, so as a person. So capital letters. You'll notice capital letters all the way down there for all the units because they were all named after people. Okay, so just to review what we said so far. So current is the rate of flow of charge. In a metallic wire, the delocalized electrons are the charge carriers moving through the metal lattice. Electrons will move continuously as a result of their thermal energy. When a potential difference is applied, then the current will drift along the wire and start to flow in a single direction. When current flows in a single direction, that is DC current. Since the current depends upon the number of charge carriers moving through the wire per second, Q equals IT, this will be affected by the potential difference and the resistance, whether that's Ohm's law. The greater the resistance, the smaller the current. So if we increase resistance, we typically reduce current because we're making it harder for the number of electrons to pass through. Think of that a bit like if I if I put a traffic jam in a road, I'm going to reduce the amount of traffic that's able to travel down it, and that's the same idea. So increasing resistance generally decreases current, and because it increases the number of electron-ion collisions. Okay, so the next big thing then is understanding the difference in series and parallel. So I'm just going to show you some little animations. You can, I'm going to pose some questions to you. You can pause the video, consider these, and I'm going to talk through the answers reasonably quickly for afterwards. So if you're revising in a rush, feel free just to kind of skip to the explanation. So the first question is, you can see here we've got a simple circuit with a power supply. So a series of cells, which obviously combined as a battery, and a resistor. So just to explain, the squiggly line here is a different way of drawing a resistor circuit symbol. It's not the kind that you will have to do in your exam. That is just a rectangle, but it's just an alternative that's shown on this animation. That is just a resistor. And on the second one, you've got 2 resistors in series. So have a think about the question: what is the effect of adding that second resistor had on the circuit? What impact has that made? Okay, and you can have a little second to think about that. So before we go through that, here's another one. So here is the same example you just saw, but this time we've now got added another 2 resistors, but in parallel. And again, you can think about this. So here are some questions to just consider. We're going to go through the answers in a minute. What happens to the current when it splits into the parallel paths? What happens to the energy of the charges when that happens? Where does that energy go? Which configuration, the top or the bottom one, has the greatest resistance? So have a little think about those and we'll go through the answers now. So, in terms of what happens to the current when it splits down the parallel path, you'll notice that it's splitting in this example equally. Now that's not necessarily always going to be the case because current will take the path of least resistance, but what we're saying is that these 4 resistors are all identical. So because there is no bias towards one direction or the other, the current is splitting equally down the path. So anytime the resistance is equal, current will split equally. If one path has more resistance, then the less current will go that way, just like a traffic jam. The energy of the charges, when it splits, you'll notice there is no change. So in other words, the energy in these diagrams is shown by the red colour. And you'll notice that there is no change when it splits down the path. It's still red. Think of this again like traffic. Think of this like the motorway. You've got the M5, M6 junction, so the road is travelling, all the cars are driving at 70 miles an hour, but half of them are going to go down the M5 and half are going to go down the M6, but they're still all travelling at 70 miles an hour. So remember, that is like indicative of the energy that they are carrying with them. So they're still carrying the same energy, it's just that there are fewer cars or fewer electrons travelling down each pathway. So it affects the numbers, but not the energy they take with them. And then where that energy then goes, well, that energy isn't transferred until it meets a transducer, which in this case is the resistor. Transducers just convert energy into a new form. So in the case of a resistor, they would transfer that energy into thermal energy. They would just get hot. So that energy is transferred to kinetic energy behind in the lattice as a result of those collisions. That increases the temperature. And then of these two, which has the greatest resistance, that is the one where they're in series. So even though there are 4 resistors in the bottom example, you can see that actually the resistance is less. You can tell that by the fact that the current is travelling faster. Because remember, current is the number of electrons per second. So when you add things in parallel, you actually reduce the resistance. And the reason for that is you're basically relieving the flow of the total charge by providing more options, more pathways for it to kind of go down. The metaphor that I always use for this is like the idea of multiple food outlets. So in our school, we obviously have the canteen, and then we have the pasta parlour and the wrap shack. And on a day where they're all closed apart from the canteen, it's much busier, it's much harder. But when you add alternative options, you add alternative pathways, the traffic everywhere gets eased. And so anytime you add stuff in parallel, resistance is reduced. So to summarise all of that, one of the most important slides that we're going to cover in this is you have to know the difference between series and parallel for the 3 main components: current, potential difference, and resistance. So in series, the current is the same at every point in a series circuit. Every single point, it's the same because it's like one track. Think of like a F1 racing track circuit where the cars, there's X number of cars that are on there, so let's just say there are 24 cars on the circuit at any one time, and they are confined to that circuit, they can't go anywhere. So if you added them all up, you would say that overall at any one point there's always going to be the same number on that point on the track. So the current is the same everywhere in series. Whereas the potential difference, the energy, is split between each component. So for example, if I've got a 12 volt battery and I've got 2 identical bulbs, each will get 6 volts of that energy. That energy is split between each of them. If I had 3 identical bulbs, it would be split 4 volts, 4 volts, 4 volts, because what goes in must come out. But the energy will be split between each component. That is the way that series kind of works. And the resistance is the sum of all the resistors. So in series circuits, every resistor you add resistance. So you just add up the total resistance by adding up each resistor. Now in parallel, because the current splits down each pathway, that obviously has the effect of reducing the current in certain places. But obviously they all have to join back up again at the end. It's really important you understand that. So it will split down each pathway, but on each pathway, each path on, or each loop on a parallel circuit will have the same energy. So if it's 12 volts that are going in, then each path, for example, will have 12 volts as well. It's not that it will be split 6 on one path and 6 on the other. So if I've got, say for example, 2 identical bulbs, but instead of connecting them in series, where my 12 volts would be split 6 volts and 6 volts, if I connected them in parallel, they would both receive 12 volts, but they would just be receiving a lower current as they do that. And then to summarise the idea of resistance, you don't need to know the actual equation for resistors in parallel, but you do need to know the idea that when you add things in parallel, resistance decreases. So the total resistance will always be smaller than the smallest individual resistor, because you're always lowering resistance when you add things in parallel. So very important to understand that. Please take a moment to pause this slide, really think about it, really consider it. If you don't understand the difference between series and parallel, it is something worth spending time on prior to your exam. So, just to build on some other ideas that are going to help us pick up marks. So resistance, we've already talked about, is really to do with this idea of electron-ion collisions. So anytime we have electron collisions between the electrons and the ions, that basically is what resistance is. Anything that's going to increase those number of collisions will increase resistance. So if you kind of consider this graphic that kind of shows the relationship, it's quite a popular one. When we think about Ohm's law, we can think about the idea that current is how much is travelling through the wire, voltage is how much energy, how much push it's being given, and resistance is what is preventing that current from just flowing freely down the wire. You can see in the animation on the bottom left about the electrons colliding with the ions as they go through. So, the equation for Ohm's law we've already mentioned, but it's important we also mention the practical. And in this topic, there are basically two practicals you will mainly be focused on, but they can both be summarised very similarly in terms of like the circuit diagram. So you can see one example of a suitable circuit diagram here shown. So in this case, we have a variable power supply, some electrical component we're investigating, in this case a wire, and in order to investigate it, we must connect our ammeter in series and our voltmeter in parallel. For the purposes of the two practicals you could be investigating in this topic, one of them is you could investigate different components, so do different IV characteristics, which I'll show you in a minute. So one is you can investigate a wire, you could also investigate a bulb, a thermistor, or a diode. Another alternative is you could investigate the actual wire. So you could vary the length of the wire, you could vary the thickness of the wire, you could vary the temperature of the wire, and you could see what effect that would have on the current and potential difference, and therefore the resistance, which is what we're interested in. So an alternative to this diagram is if you don't have a variable power supply, you must have something that is variable. So if you don't have a variable power supply, please just include a variable resistor next to it, because the reason you will do that is by adjusting the variable resistor, you change the voltage or the potential difference across the thing you're investigating, and then you measure the current, which is why when we plot an IV characteristic, potential difference is on the x-axis because that's the thing we change, and current is on the y-axis because that's the thing we're actually measuring. Okay, so when we do that, we can determine Ohm's law, which you've already seen as an equation, but Ohm's law in words is that current is directly proportional to potential difference, provided physical conditions like temperature remain constant. In other words, Ohm's law only applies when we maintain constant resistance. And you have to be able to do graphs for this for, as I've said, a fixed resistor, a bulb, a thermistor, and an LED or diode, which I'll show you in a moment. This is the actual equation, as we've already mentioned, so I'm not going to dwell too much on this, but it is the most important equation. It is the one that will come up the most in your exam. Please make sure you are familiar with it and use it repeatedly. So here is the IV characteristic for a metallic conductor, in other words a wire. So you've got current on the y-axis, potential difference on the x-axis. The three main things you need to know about this. The first is the shape. So the fact that this is a straight line and it goes through the origin is the two things that are needed to tell you Ohm's law, which is that current is directly proportional to potential difference. So anytime you have a straight line going through the origin, that tells you something is directly proportional. In this case, current and potential difference. The next thing you need to know about this graph is that obviously because it's a straight line, that is indicating to us the resistance is constant. But in terms of the actual meaning of it, the gradient of the graph is how we work out resistance. But because resistance is voltage divided by current, and gradients are always y divided by x, the gradient is actually equal to 1 over r. So it's the reciprocal of resistance, not resistance itself. So in other words, if this line was to get steeper, the resistance would actually be getting less. So it's important to understand that idea, and we'll see that expressed in a moment. So, linking all these ideas together, one of the key things that we have to therefore do, and I've mentioned this already, is be able to explain the link between current and resistance. Really, really key. So, I'm going to show you the mark scheme for this question in a moment, so you can have a look at it. But I just want to talk through in sort of bullet point form what the key ideas are. This question is, explain how the resistance of the filament changes when current passes through it. We've got to use ideas about ions and electrical current. So just to reiterate these points I've said already, but this is like a really key explanation I would encourage you to really make sure you note down and learn prior to the exam. So anytime we increase current, that causes an increase in the number of electrons travelling down the wire, and therefore will increase the number of electron-ion collisions. Every one of those collisions transfers a little bit of energy, and so that energy is transferred to the ions and cause them to increase their kinetic energy. They're going to be moving around more. Temperature is defined as the measure of the average kinetic energy of particles. So if we're increasing the energy of those ions because of those collisions, we will increase temperature. So increasing current causes the wire to get hotter and temperature increases. The reason is because there's an increase in electron-ion collisions. So really important that you use that phrase, electron-ion collisions. The result of that increased temperature, as I've said, it means you increase the kinetic energy of the ions, so they will be vibrating more, because in a solid, those particles are in a fixed position but are free to vibrate. Okay, that's how their energy is kind of expressed. And the consequence of that is, if you have more vibrations, that is further going to increase the number of electron-ion collisions, which then causes more resistance. Because I always use the metaphor here of like a goalkeeper that's standing on the line, but it's like bouncing around everywhere, is much more likely to stop the ball passing them than one that stood absolutely still, stone cold, like on the line. And so with the ions, that's what you can imagine. When they get hot, they start vibrating, they're moving around a lot more, they're a lot more likely to kind of stop something passing them. Another metaphor you might use is, imagine you're walking down a really long corridor, and there's loads of people stood in the corridor, but they've all stood still. And you just got to walk down the corridor and not bump into them. Now imagine if we then said like go, and all the people have just got to like sort of jump side to side, like and like try and stop you. You've got to go down the same corridor and somehow not bang into them. That's obviously going to be much harder. So increasing current increases temperature. That's really, really key, because anytime you have high current, that increase in temperature increases energy loss. And that is really important at the end of the module. I'm going to circle back to that. That's because you get more electron-ion collisions. That causes more vibrations, and that therefore increases resistance, and you get this kind of loop. So here is the actual mark scheme for that question. You can see the ideas that I've just talked about expressed, but not necessarily quite as sequentially as, but it's really important to take a second to read this, have a look at that question, make sure you can answer it for your exam. So other factors that affect resistance then, all of these you could be asked to investigate, okay, are the thickness of the wire, the length, the material of the wire is actually made of, and obviously temperature. We talked about temperature a second ago, about the fact that increasing temperature increases kinetic energy, increases the number of vibrations, therefore increases resistance. The material will obviously vary based upon the number of conduction electrons and other stuff like that, but different materials will have different electrical conductivity. Length of wire is very easy. The longer the wire, the bigger the resistance. Just think of it like the longer the journey, the harder it is. The one that stands out here is the thickness, or the cross-sectional area of the wire. The thicker the wire, the lower the resistance. Really simple analogy. Imagine that you're in your exam hall and there was a fire alarm and everybody's got to walk out of the doors, but imagine the examiners have locked one of them shut. So everyone's got to walk through one door, versus if both doors were swung open, people would be able to exit much more quickly. And that's the same basic idea. The thicker the wire, the lower the resistance, because there's just more space for the electrons to move around. Another thing to think about here would be like a water drain versus a hose pipe. Hose pipe has got a very, very small area, it's very thin, so all the water is forced out, it's much harder for the water to get through. Like a storm drain is designed so that the flow of water that's going through it is much smaller compared to the overall area, and so it flows through freely without too many issues. So then, just looking at the other IV characteristics, okay, so we have here the one for a filament bulb, okay, you can see the basic shape. So you do need to be able to sketch this shape. It is mentioned explicitly in the specification you saw at the start. The key feature of the filament bulb is you can see it gets flatter. Remember, the gradient of an IV characteristic is 1 over resistance. So as it gets flatter, that means the resistance is actually increasing. So remember, it's the opposite. So the resistance is lowest at the start of this, where the line is steepest. The reason for this is because it gets hotter. So when you turn a bulb on, the current goes through it. Current is going to generate that increase in temperature over time. As the temperature increases, that increases resistance, increases the number of electron-ion collisions. So the hotter the bulb gets, the higher the resistance, hence why the graph plateaus, the way it starts to flatten out. The opposite of that, if you focus on the diagram on the right here, is a thermistor. So obviously that's the exact opposite of a bulb, because as temperature increases in a thermistor, resistance decreases, so it's the exact opposite shape. So you need to be able to contrast those. There is an alternative graph on the left which shows the resistance against potential difference for the same filament bulb you just saw a moment ago, and notice how initially the resistance is pretty constant. If I just go back, that is shown by the fact that initially this is almost a straight line, and then the curve starts to kick in as the resistance starts to increase. So we get this alternative shape, but don't stress too much about that. It's more like an application problem. And particularly for maybe for the higher paper, it might be something to be considered. The last IV characteristic is the diode. Diodes only allow current to flow in one direction, so the key characteristic here is the fact that it is a positive and negative direction, and the negative is 0, because no current, shown by the purple line, is able to pass through. In the positive direction, over a certain threshold voltage, current will then flow freely, can't get my words out, and therefore the gradient goes very steep because resistance has decreased massively. Okay, so make sure that you know that shape as well. Okay, so we're on to the final bits of the module now, and this is what I call the quick fire easy marks, because There are lots of things here that you can learn quite quickly and pick up some easy marks. You will definitely get questions on these. They'll be short 1 mark, 2 mark questions, but a really good place to pick up some easy marks if you're struggling the night before your exam. So the first thing is you need to know the difference between AC and DC. And to be really clear, you have to know 4 things about both. Once you know those 4 things, you are done. That's all you need to know. You need to know what does AC and DC stand for, what types of devices use AC and DC, what's the definition of each, and what would be the shape of the voltage time graph for each one. Those are the 4 things, so let's show you those. So, what do they stand for? AC stands for alternating current, so you need to know that first off. And what that means is that current doesn't travel in one direction around the wire. In AC, an alternating current, the current is alternating. In other words, it's constantly changing direction. So that 3-word phrase, constantly changing direction, that is the phrase that you want to try and use for AC. Constantly changing direction. Anything that is plugged into the mains electricity is AC. So it's anything plugged in. That's the type of device you're dealing with. Because as we'll talk about in a minute, one of the key facts that you need to know about the national grid is it's AC. The graph for AC is a sine curve, okay? Because AC is constantly changing direction, so the voltage is constantly changing, which is why it gets a sine curve shape. And this also gives us one of the other features of mains electricity, which you have to learn, which is it has a frequency of 50 Hertz, which I'll come back to in a minute. So those are the 4 things for AC. You need to know it stands for alternating current. It means that the current is constantly changing direction. Anything that's plugged in is AC, and you can see the shape of the voltage time graph. DC stands for direct current. Anything that is battery powered, so like for example your mobile phone when it's not plugged in, that is DC. And DC, the current only flows in one direction. All of the examples of current we've talked about up to this point in the module have all been about DC. We've always been imagining an electron just flowing in one direction. We haven't actually really got into the technical elements of AC, and you won't be asked about those, so don't worry about it. You just need to know what they stand for and know that mains electricity in particular is AC. The graph for DC is really simple. It's just a straight line, and it's a flat line because the current is constant. It's just staying at the same level, it's constantly going in the same direction, constantly at the same level, nothing's changing that. So remember that phrase for AC, constantly changing direction, doesn't apply for DC. DC means in one direction, okay? Only. So that's the difference. Those are the 4 things you need to know. Once you revise that, you've got that down. The questions they ask you in your exam will only come effectively from those key facts that you need to learn. And that is the same slide again, just with a different background. So mains electricity then. There are 3 features of mains electricity that you just need to rote learn. Okay, in the UK, these are the 3 features you need to know. The voltage that comes out of our plug sockets is 230 volts. It has a frequency of 50 Hertz, and it's AC. This very often comes up as like a multiple choice question where you've got 4 options, and they're like, which of these is correct for the UK? And there's obviously a version of this where it's like 230, 50, and DC, which is wrong, because that's only for battery powered things, not from the mains. There's a version of this where it's a different voltage. Now, in Europe and America, it is a different voltage. It's not 230 volts, but in the UK, it is 230 volts. So very often, for example, 110 volts is used there as a distractor, which would be true in other countries, but not in the UK. And then again, sometimes I might just give you a totally different number for frequency, but it is 50 Hertz. That is what the national grid is maintained at in the UK. So 3 easy facts to learn. You just got to rote learn them. There's nothing else to it. That's the key 3 features of mains electricity. Now, with that, the next thing you need to know, again, easy marks, is you need to know the bits about how a plug is wired. Okay, so this is a diagram showing it. Okay, and I'll put up all the points of the diagram here, so you can pause the video at this point, take a second to consider the diagram. Obviously, in your exam, your diagram is not going to be printed in colour, so any colours will just be stated in words. You have to sort of take it for granted what the colour is. But you do need to know the colours, but I'm going to summarise this in a table in a second because it's the easiest way to revise it. But take a second to consider it. There's basically 2 main safety features I just want to draw your attention to at this point in the plug. The first is the fact that there's an earth wire which is connected to an earth pin, and that, as we'll see in a second, prevents the casing becoming live, and that's a safety feature. The other safety feature is that the brown wire, that will always go if there is a fuse inside the plug to the fuse. Because the brown wire, as we'll talk about in a minute, is what carries the initial voltage into the plug, and then it goes through the fuse. The fuse has a very thin wire inside it, which if the current goes too high, current will increase temperature, that will obviously get hotter, and then the resulting wire will melt in the fuse, that was what we would mean by a fuse has blown, and that will obviously break the circuit and will prevent the whole device like overheating and potentially catching fire. So that's the job of a fuse. And then obviously the blue wire, as we'll see in a minute, completes the circuit. But that's the way you can tell them apart. Like visually, the live wire will always be linked to the fuse. The neutral wire just completes the circuit, so it's just linked to the opposite pin. Okay. Now, summarising this in the most efficient way possible is a table. So you need to know the 3 wires, you need to know the colours. So the live wire is brown, and that is the one that has a potential difference of 230 volts, because that is the thing that carries the energy effectively into the plug. Now it's possible to have a 2-pin plug. Okay. If you have a 2-pin plug, there's no earth pin. So you always have a live wire and a neutral wire. The neutral wire is blue. I always remember that from the think sense of like blue being calming, like tranquil, I think of the sea. That has a voltage of 0, right? And the reason is its job is it just completes the circuit. So all of the energy effectively is gone at that point. It's gone out into the device. So the live wire kind of transmits the voltage to the device. The device uses that energy. The neutral wire just completes the circuit. And then we have the earth wire, which is green and yellow. I try to remember that with sunflowers. I think of the sunflower, I think of the green stem, the bright yellow leaves. That's how I remember it, kind of like earthy vibes. Okay. Again, that's got a potential difference of 0. You need to know the function of each one. So a live wire carries the potential difference. Remember, it's AC that it's carrying. Blue wire completes the circuit, and the earth wire is the safety wire, which prevents the casing becoming live, prevents you getting an electric shock. Okay. So if it becomes charged, the current will hopefully not pass through you when you touch it and get an electric shock. It will be ground to the earth and will dissipate that way. So that's the same information there. We're on to the very, very last bit of the module now, which is the national grid. So I'm just going to mention some really brief things really quickly. You need to have a general sense of how the national grid works. We talked about the features of the national grid. When the electricity comes out at the plug socket at the end, it is 230 volts, it is 50 hertz, and it is AC. But in order to get from the power station, a couple of extra steps have got to happen, because we want to transmit as much energy from the power station to your home. We don't want to lose energy along the way. So the problem is if we just transmitted it at the level we want it to come out in your plug socket, 230 volts, 50 hertz, AC, the problem with that is the current would be too high. And so if we're transmitting that, say, 30 miles through some overhead pylons, an awful lot of energy is going to be wasted as heat. And effectively, those overhead pylons would become really fancy heaters in the sky, and the like animals that are like, on the fields underneath them will just be having like a nice gentle roasting. And we don't want that. We don't want to waste energy as heat. So what do? We use transformers. So you don't need to know a great deal about transformers, but you do need to know what their job is. Transformers have the effect of making that energy transfer more efficient. They do that by massively increasing the voltage as the energy is being transferred, and in doing that, by keeping the power the same and increasing the voltage, you massively reduce current. Reducing current means that there's less heating, there is less energy wasted. That is a good thing. But the problem with that is if we just did that, if we took the energy from the power station, we increased the voltage, but then we just went straight to your home, then you would go to put your plug in the plug socket and like sparks would fly from the wall towards your plug, and that would be disastrous. So we have to have a second transformer, a step down transformer, which before it comes out into your home reduces the voltage back down to the 230 desired level that we want, so that it's safe at the point of use. So that's kind of the overall process. So a little bit about transformers. Transformers consist of 2 coils of wire bound around a iron core. We have a primary coil and a secondary coil. The 2 types, which is step up and step down. In a step up transformer, the first coil has fewer coils and the second one has more, so the voltage increases between the 2. Transformers only work with AC. They only work with alternating current, because if you remember, alternating current means the current is constantly changing direction. And although this is not on the first exam, any constantly changing current also has a constantly changing magnetic field. So that's covered in the magnetism topic for paper 2. Constantly changing magnetic fields can induce another current in the secondary coil. You're not going to be asked to explain transformers, but this idea of constantly changing current having a constantly changing magnetic field which produces another constantly changing current, using the word constantly changing there being the key thing, that is basically how transformers work. They rely on that idea. So You don't need to know the explanation of that, you just need to know the outcome. You need to know there are two types of transformers, one increases potential difference and one decreases it, step up and step down. Okay, and obviously a step down has fewer turns on the secondary coil, hence why the voltage drops. And the most important idea, which I want to circle back to, is, well, why do we do this? It's because we want to reduce power loss. So to summarise the key ideas we've talked about in this masterclass, when current passes through a wire, that causes a temperature increase. That temperature increase causes energy to be lost to the surroundings. That is bad. Remember, we talked about the power loss equation earlier, the I squared R equation. That equation contains the two factors that are going to lead to power loss and energy loss, which is current, which is doubly bad because it's squared, and resistance. We can't do a great deal about the resistance of the wire because they have to be long and they have to be made out of a certain material. We can obviously make sure that material is a good conductor, but we can do something about the current, which obviously has a better effect because it's squared in the first place. So we do that by transmitting the electricity with obviously a constant power, but high voltage and low current. That's how we transmit it through the overhead power lines to be as efficient as possible. That is the end of the electricity module. Hopefully that has been helpful to help you prepare for your exam. There are other masterclasses available for paper 1, so please make sure you check those out on each of the modules. We've got energy, we've got electricity, we've got matter, and we've got radioactivity. So please give those a watch because there are definitely easy marks that can be picked up by just revising a few simple things. There is a lot of content in this module, but if you just focus on some of the key elements that we've talked about in this video, I promise it will help boost your grade. So I really hope you found this useful, and don't forget to subscribe and all that jazz. Thanks very much. Best of luck.